Hello and welcome back. In the first two chapters, we've talked about why space is important to us and how it affects our lives. We know the history of space exploration and the Air Force's role in the space community. Now you can understand what challenges and sacrifices are made by people just like you in order to explore space. Now let's talk about being in space. We'll discuss the cosmic view that allows us to think about ourselves in relation to Earth, the Moon, the solar system, galaxy, and universe. We'll be able to answer the question, where is space? And understand where space begins and ends. Then we'll look at the solar system and the cosmos for more information on these two places in space. In the next two lessons, we'll discuss details of the space environment and understand how tough it is for people to live in space. When we learn about the cosmic view or perspective, we need to understand what we mean by the cosmos. The beautiful night sky has always generated a sense of wonder and speculation. The concept of the cosmos didn't come about after people discovered instruments that can look into space. We know the Greeks were thinking about the cosmos even before Socrates. Their definition of the cosmos has stood the test of time and is pretty much the same one we use today. The cosmos is a complex, orderly system which is the opposite of chaos. Most of us think our lives have moments of chaos. For example, wars or natural disasters like hurricanes, floods, or volcanoes. On this slide, you can see an optical image of the cosmos, in which Earth is just one tiny bright spot. We'll come back to the cosmos later. But first, let's look at where space begins and how Earth fits into the solar system. Have you ever wondered exactly where space is? You may have said, up there, or out there, or even way, way out there. But no one has concretely defined where Earth's atmosphere ends and space begins. For our study, we'll say space begins at an altitude of 130 kilometers or 81 miles. This is the altitude where satellites can maintain orbit at least for a short time. So, if you were to think about Earth as a peach, most satellites would be just above the fuzz. According to NASA, people who get to an altitude of just over 57 miles earn astronaut wings. Would you be interested? We just spoke about the definition we'll use to study space, the altitude where an object can maintain orbit. But the Air Force and NASA have different definitions of where space begins. The Air Force proudly pins astronaut wings on a person who reaches an altitude of over 57 miles, but it doesn't require a person to go into orbit. Only recently did NASA award the X-15 pilots well-deserved astronaut wings for their achievements in paving the way for the first men in orbit. Now that we've looked at two definitions of space important to our study, let's look at the solar system and in particular, the sun. Do you want to know some amazing facts about the sun? Every second, the sun generates enough energy to supply the entire U.S. for 624 million years, and 600 million tons of hydrogen are burned per second in nuclear fusion on the sun. We won't go into any detail about nuclear fusion now, but we're going to talk about two of its byproducts, electromagnetic or EM radiation and charged particles. We know the sun generates energy, but what's the main form of that energy? If you said electromagnetic radiation, you'd be right. We feel that radiation on our faces as light and heat when the sun is out. But how do the sun's light and heat get to us? Electromagnetic radiation is a way for energy to get from one place to another. It travels in waves. The sun's EM radiation has many wavelengths such as infrared or heat waves, visible light waves, ultraviolet waves that we protect against with sunblock and sunglasses, and X-rays like the ones you get when you go to the dentist. Gamma rays and radio waves are two other forms of EM radiation waves. We know the sun sends energy in many forms. This amazing artist's image shows the European Space Agency's Infrared Space Observatory underway in November 1995. This satellite, launched on board an Ariane 4 rocket, was on a mission to measure and analyze infrared or heat wavelengths. We study the sun because it's the center of the solar system. So what do we mean by the term wavelength? We said earlier that energy gets from one place to another through waves, and the sun's EM radiation has many wavelengths within the electromagnetic spectrum. If we had an EM wave, as shown here, we can measure the distance between the two peaks called wavelengths. For example, visible light is only a small sliver of the electromagnetic spectrum, and a rainbow shows us how change in wavelengths can vary the colors we see from red to violet. We can understand how different wavelengths of EM radiation are by looking at these two amazing photos of gamma rays and radio waves. Gamma rays have the shortest wavelength, and radio waves have the longest. Electromagnetic radiation wavelengths are all around us. We said earlier that nuclear fusion on the sun burns 600 million tons of hydrogen every second. The intense heat from nuclear fusion breaks atoms into basic building blocks of protons, electrons, and neutrons, shown here. The neutrons quickly decay into an electron and a proton. So, the sun is a source of protons and electrons. The sun's magnetic field acts like a big magnet, driving these particles toward Earth at high speed. We call this the solar wind. Occasionally, areas of the sun's surface erupt in the solar flares you see here. The sun is huge, but look at the size of the solar flare. Highly explosive solar flares are many times more powerful than a nuclear weapon, and they cause vast amounts of energy and material to speed away from the sun. Sometimes solar flares arrive at Earth's surface, but fortunately, only a small number reach Earth. Besides the sun, the solar system contains planets, dozens of moons, and thousands of asteroids. However, information from Hubble Space Telescope has prompted scientists to reconsider the definition of a planet. In this course, we'll focus on how Earth and the sun affect objects in space. The sun holds the solar system together with its gravity, and Earth has an atmosphere and a magnetic field. Other planets may or may not have an atmosphere and magnetic field. Because distances in space are so huge, let's bring them down to a level we can understand. If the sun were the size of a 1-inch marble, the nearest star to our solar system, Proxima Centauri, would be more than 932 miles away, or about the distance from Denver to Chicago. These are still gigantic distances, but if you put your mind to it, you can get an idea of just how big space is. We just mentioned Proxima Centauri, the next closest star to the sun in the galaxy, which is about 4.22 light years away. Well, what exactly is a light year? A light year is the distance light travels in 1 year, or about 5.88 trillion miles. So, if one of our interplanetary spacecraft were to head toward Proxima Centauri and travel at 35,000 miles per hour, it would take about 80,000 years to get there. Chances are good that in our lifetimes, we probably won't be visiting Proxima Centauri. When you look out at the night sky, you can see space is really big, but that doesn't tell you how big. This diagram gives you an idea of the solar system's size. Imagine the entire solar system was the size of a large marble, about 1 inch in diameter. The Milky Way galaxy would be 1,266 miles across. So, if the solar system were the size of a marble in Denver, Colorado, the Milky Way galaxy would cover most of the western United States. At this scale, the nearest galaxy would be 25,000 miles away. The solar system is only part of the Milky Way galaxy, and it's about one halfway between the center and the edge of the galaxy. The Milky Way, with all of us, spins slowly about its center once every 240 million years. We call this rotation of 240 million years one cosmic year. This figure gives us an idea about galactic distances, but even with the numbers to back them up, it's still difficult to imagine these distances. Please answer the questions on this slide. If you have trouble with any of them, just go over the material and try again, or ask your teacher for help. In this clip, you'll see Earth surrounded by its magnetic field lines. Then you'll see the solar wind coming from the sun. Earth's magnetic field protects us from much of the solar wind. Even so, particles and radiation from the solar wind enter Earth's atmosphere through the north and south poles. The result is the aurora, or northern and southern lights, that you'll see near the end of the clip. Well, this was an exciting section that helped us learn about the space environment. We talked about the cosmic perspective and how we can think about ourselves in relation to the solar system, galaxy, and universe. We can answer the question, where is space, in two different ways and understand how and why they differ. And we can identify where space begins. We learned how big the solar system and cosmos are in relation to Earth. Next, we'll take a closer look at the space environment and how it affects spacecraft and people in orbit. This is going to be some really exciting information for all of you who have hopes of going into space or being a part of the team that gets us there.